Welcome to The Explainer. Today, we are diving deep into one of the single biggest challenges in AI. How do you actually train these massive models that are changing our world? We're going to break down a really fascinating new research paper that introduces a tool designed to make that whole process a lot smarter. So here's what we've got on tap. We're going to start with the big picture problem, then we'll meet the current tools of the trade. After that, we'll uncover two sneaky hidden flaws that are holding them back. And finally, we'll see how this new solution, called Root, tackles them head-on with some pretty clever tricks. All right, let's jump right in. Okay, first things first, let's set the stage here. When you're training a model with billions of parameters, it's not just about throwing more computers at it. You have to imagine it's like a journey through this unbelievably complex, high-dimensional landscape, and you're searching for one single point in all of that chaos that represents the best possible performance. Now, the key to this whole journey is something called the optimizer. The best way to think of it is as a super sophisticated GPS for the AI. It's the algorithm that guides the model during training, telling it which way to go to get smarter and more accurate. And believe me, the choice of optimizer is absolutely crucial. It affects how fast you train, how good the model is at the end, and even the financial cost, which we're talking millions of dollars here.
So, who are the current champions in this field? Well, for a long time, there was one clear favorite, but, the game is changing. Let's meet the key players on the board.
For years, an optimizer called Adam was basically the industry standard. It was the go-to, adapting its approach for every single parameter inside the model. But as models got bigger and bigger, new methods like Muon came along. Muon's a little different. It takes a more holistic view, kind of treating entire layers of the model as single objects. These are really powerful tools, but as this research shows, they're not perfect. And this right here, this brings us to the real core of the story today. The source paper we're looking at identifies two hidden but really critical flaws that can throw even these advanced GPS navigators completely off course during that training journey. Okay, so problem number one is something the researchers call dimensional fragility. The best way to wrap your head around this is to think of it as the one-size-fits-all wrench problem. Imagine you're trying to fix a whole car engine, but you've only got one size of wrench. Sure, it might work okay on a few bolts, but on most of them, it's going to be clumsy and just plain ineffective. And this table, this just illustrates the problem perfectly. It shows the mean squared error for the Muon optimizer. Just think of that as a score for how wrong the model is, so lower is always better. Now check out the difference between the square and non-square matrices. With the standard fixed method, all the errors are kind of in the same ballpark, right? But when the method adapts to the specific shape of the layer, just look at what happens to the error for the non-square ones. It drops by over 100 times. This is proof that the one-size-fits-all approach is just failing, leading to really inconsistent results depending on the layer's shape. The second big flaw is outlier noise. So let's go back to our GPS analogy. Imagine you're driving along and your GPS suddenly starts screaming, "Turn into a lake." That's an outlier. These are basically rogue data points that create these extreme directional signals or gradients that just confuse the optimizer and can totally destabilize the entire training process. This slide does a great job of visualizing what that looks like. It's called a QQ plot, which is just a fancy way to see if your data is behaving like it's supposed to. That straight line in the middle, that represents a perfect, clean signal. Now, the blue dots are the actual data from the model's training. See how they follow the line pretty well in the middle, but then they just go flying off in the corners? Those are the troublemakers. Those are the outliers screaming, "Turn into the lake." So with these two major flaws on the table, the researchers behind this paper went and developed a whole new optimizer specifically designed to solve them. Let's meet Root. So this is a super simplified look at how the Muon optimizer works. It calculates a direction, it builds up momentum, then it finds the most efficient path forward using this geometric process called orthogonalization, and then it updates the model. It's a solid process, but as we've just seen, it's flawed. Now look at what Root does. This is so clever. It just slips two crucial new steps right into the middle of the process. Before it does anything else, it actively finds and separates those noisy outliers we just talked about. Only then does it apply a smarter, more robust version of that orthogonalization step. Basically, it cleans the signal before it tries to find the path. That's the core innovation right there. So let's just boil it down. The crucial point is this. Root directly attacks the two flaws we just went over. To fix that dimensional fragility, it creates a custom tool for every layer shape, like having a full wrench set instead of just one.
And to handle the outlier noise, it uses this smart filtering technique to just ignore those turn into a lake commands.
Of course, all this theory is great, but does this new, smarter navigator actually work in the real world? Well, the researchers put Root head-to-head with the current champions to find out.
This chart shows the final training loss after training a 1 billion parameter model on 10 billion tokens of data. And remember, with loss, lower is always better. It means the model found a more optimal solution in that big, complex landscape. And as you can see, Root consistently gets a lower final loss. It found a better spot on the map.
And this is the real payoff. I mean, finding a better spot on the training map is only useful if it actually creates a smarter model, right? So here, the models were tested on a whole suite of really tough academic benchmarks. And across the board, Root achieved the highest average score. It outperformed both the classic Adam-W and the more advanced Muon optimizer. This is pretty clear proof that making the training journey better leads to a more capable AI at the end.
And the authors of the paper, they don't see this as just some small, tiny improvement. They actually believe this is a fundamentally new way of thinking about how we build these crucial GPS-like tools that guide all of AI development. So why does a slightly better optimizer matter to you and me? Well, because more robust and more efficient training means we can build more powerful and more reliable AI systems. This could lead to breakthroughs in, everything from medicine to creative tools. And we could get there faster and probably at a much lower cost. It's really about accelerating the pace of innovation, safely and effectively.
And that leaves us with a pretty fascinating thought to end on. As we're all in this race to build bigger and bigger AI models, maybe, just maybe, the next great leap forward won't come from just adding more data or more computers. Maybe it'll come from the clever, robust, and elegant little algorithms that actually teach them.